Our next speaker is Professor Youl Lee from Busan National University, and he will tell us about diquandles and invariants for oriented dichromatic links. So please, you can start exactly in time.
Yeah, thank you very much for your introduction. First of all, I'm very glad to join this conference, and I'm very happy to meet you, all of you. Today, I would like to talk about the diquandles and some invariants for oriented dichromatic links. And this is a joint work with model prime Sheikh. So let me start. Here is outline of today's talks. First, I introduce some basic terminology of dichromatic links, and then I recall the quandles and the biquandles. And next, I introduce the dicays and diquandles. Actually, diquandle is the main subject of today's talks. And finally, I introduce diquandle colorings for dichromatic links. Actually, the number of diquandle colorings gives some numerical invariant for dichromatic links. Dichromatic links is a smooth embedding of n circles in 3 space that has 2 colors, where the 2 colors are usually represented by the labels 1 and 2. The dichromatic links is represented by dichromatic link diagrams in the plane as usual in the classical case. Actually, which is a classical link diagram that has the labels 1 or 2 for each component, and vice versa. 2 dichromatic links L and L prime are equivalent if they are ambient isotopic and preserve the component of the labels. So that is to say, there exists an orientation and a label preserving homeomorphism H, and such that H send L to L prime. Then 2 dichromatic links L and L prime are equivalent if and only if their diagrams D and D prime are transformed into each other by a finite sequence of Reidemeier moves, which preserves the color of each component and ambient isotopes of a plane. So this is a Reidemeier move type 1, and this is 2, and this is the third. In these moves, there is labels here, okay? Some labels. So this moves preserves a label. That is important here. Let L be a dichromatic link in 3 space of n component. If each component of L is oriented, then L is called oriented dichromatic link. The oriented dichromatic links in R3 is represented by oriented dichromatic link diagram, which is a classical oriented link diagram that has the labels 1 or 2 for each component. Okay. And similarly, and the two oriented dichromatic links L and L prime R3 are equivalent. They are ambient isotopic and preserved component labels. Oriented right-and-left move are type 1, type 2, and type 3. Okay, so in this move, we put orientations for each strings. And also, each string have some labels, 1 over 2. ij means 1 over 2. So this is called, these are called labeled randomized moves. So here are some oriented dichromatic link diagrams. Okay? So actually, the ordinary classical link, oriented classical link diagram, and with some labels here, like this. Okay? Actually, spatial class of dichromatic links gives nuts and links in the solid torus. One trivial dichromatic link in 3-sphere is a dichromatic link having at least 2 components, one of which is unknotted and labeled 1, while and all other components are labeled 2. An important class of one trivial dichromatic links is the class of the 2-bridge links and the closed braid with the braid axis and cyclic periodic links with the periodic axis. Okay? And there are also some other examples. One trivial dichromatic link in S3 correspond in obvious way to a link in the solid torus. Actually, let L be a link in the solid torus. Now imagine the solid torus standardly embedded in 3 space R3, so that each core coincides with the unit circle in the plane, this XY plane. Then a regular projection of L to this plane with a hole in each center represent a diagram of L, called the punctured diagram of L. The picture is like this. We forget this component C and put here some point represent punctures, 1 punctures in the plane. Then this L part is the regular projection of the link L in the solid torus. On the other hand, compactifying the R3, the G-axis becomes unknotted circles, and the solid torus is obtained by cutting out a regular neighborhood of the component C from the 3-sphere. Then we obtain a diagram of L in S3, okay, in which C, this C, represent a unknotted component labeled by 1, like this, while the other components are all labeled 2.
So well, it is 10 a.m.
Sorry? So this gives a one trivial dichromatic link diagram in S3. Is it okay?
Yes, everything okay.
Yeah,
Please continue.
Now I introduce quandles and biquandles. Actually, the basic definitions of these algebraic systems. Okay, a quandle is a set X equipped with a binary operation delta satisfying the following three conditions. The for all X, delta X is X. Actually, for all elements is idempotent. And for all XY in X, there is a unique element Z such that X equals Z delta Y. And for all XY Z it is satisfy these self-distributive laws. A quandle X with a binary operation is denoted by this pair. We remark that the condition Q2, quandle condition 2, can be replaced as follows, right? There exists a binary operation delta inverse such that for XY X it is X delta Y, delta inverse Y is X, okay? And also X delta inverse Y, delta Y is also X. In this case, the quandle operation delta inverse is called the dual operation of the quandle operation delta. And this X and the dual operation is called the dual quandle of the quandle. Actually, this is a quandle. So we call the dual quandle. There are many examples of the quandles, as you know, the integers, and the integers are modulo n, Zn. Actually, any abelian groups are all quandles with these binary operations. And every vector space is a quandle with this operation. And every group is also quandle with these operations. On special quandle is an involutory quandle, or say a K, that is a set X with a binary operation satisfying these three conditions. And the second condition is different from the ordinary quandle, right? Note that every involutory quandle is a quandle with a self-dual operation, okay? And the operation is not an involutory quandle. And the biquandle is another algebraic structure which is set with the two binary operations satisfying these conditions. So for any X it is, it satisfies this equation, and the two binary operations are both right invertible. So right invertible means two operations satisfy and these equations. And the map H defined by this is invertible or bijective equivalently. And for any X, Y, Z, X, it satisfy these three equations are satisfied. As you know, the given classical link diagram, the coloring rule at the crossings by quandle is like this, okay? And the coloring rules at the crossings and by quandle is like this. Then this coloring rule gives some invariant of classical links in 3 space. So for example, coloring numbers and quandle cocycle invariant and so on. Of course, this quandle and the biquandle also gives some invariant for surface links in four-dimensional space by using a similar coloring rule for a broken surface link diagram of the surface links. Now I'd like to introduce the dicays and the diquandles. A dicay is a set X equipped with two binary operations satisfying the following axioms. X delta 1 and X delta 2 are both K's, involuntary quandles. And these two operations, delta 1, delta 2, satisfies these distributive laws, called right distributive laws. Also, dicay X is denoted by these triples, and these two identities are called right distributive laws. In 2020, the Eteni and Said introduced the dicay for two-component dichromatic links, extending the notion of K from the ordinary links to dichromatic links. And that result from the generalized Reidemeister moves. Generalized Reidemeister moves means Reidemeister moves with some labels, okay, describing equivalent dichromatic links. They show that the number of colorings by a finite dicay with coloring rule like this for each crossing is invariant for unoriented dichromatic links. So our purpose is considers similarly the some algebraic structure for oriented dichromatic links. So we introduce the diquandle. A diquandle is a set X with equipped with two binary operations, delta 1 and delta 2, satisfying the following three conditions. The X delta 1, X delta 2 are both quandles, and the DQ2, DQ3 is actually right distributive laws, okay, among the two binary operations, delta 1 and delta 2. Diquandle is also denoted by this triple. By definition, it is direct that every dicay is a diquandle, and which is called dicay diquandle. And also it is noted that there is a non-dicay diquandles. There are many examples of diquandle. I'd like to introduce some easy examples. Let the X delta be a quandle and the delta inverse be the dual operation of delta. Then X delta inverse is also quandle. It is immutable by definition, and X delta delta and X delta inverse are all diquandles. In this case, this diquandle is called dual diquandle of this quandle. And this equation is well known. And so X delta delta inverse, X delta inverse delta are also both quandles. So another example is X delta be a quandle and the star be the trivial operation. That is to say, X star Y equal X for all X, Y in X. Then it is immediate that these two are all diquandles, so which is called quandle diquandle. Actually, this is isomorphic to the quandles because this operation is trivial like this. Otherwise, it is called non-quandle diquandle. So, in this sense, all quandle can be regarded as diquandles. Another non-trivial example is the Alexander diquandle. The lambda be this Laurent polynomial ring in two variables t1, t2, and x be any lambda module. Then define two operation delta 1, delta 2 like this. Then it is easy to check these two are Alexander. It is well known that these two are Alexander quandles with dual operation like this. Okay. So in this case, x delta 1, delta 2 forms a diquandles, which is called Alexander diquandles. As in quandles and biquandles, any finite diquandle can be represented by matrix notations. So actually, let x1, x2, xn be a finite diquandle with two operations, delta 1, delta 2. Then this diquandle is presented by these block matrices. Okay? So M1 and the M2 matrix are defined like this. So M1 matrix is just operation table of delta 1, and M2 matrix is actually operation table of delta 2. Okay. Then finite at x 1, 2, 3, 4 with the following matrix is a diquandle of order 4. It is. And the same set with this matrix is actually non-dike diquandle of order 4. And the finite set x 1, 2, 3 with this matrix is the non-biquandle diquandle of order 3. So these examples shows that bik and biquandle and the diquandles are all distinct algebraic structures. Now consider group G2, the group of order 2, cyclic group of order 2. Then the class of G2 families of quandles gives a special class of diquandles. So to discuss this, we first remind the definition of G family of quandles. G be a group with identity E. A G family of quandles is a non-empty set X with a family of binary operations, denoted by this one, star to the G, satisfying the following actions. Okay. When we specify the family of binary operations, star G of the G family of quandles, we denote G family of quandles by these pairs. Okay. A diquandle X delta 1 delta 2 with trivial delta 1 and involuntary quandle operation delta 2, or trivial operation delta 2 and involuntary quandle operation delta 1 is called involuntary quandle diquandle. Actually, these two are trivial operation. Actually, this diquandle is nothing but the involutory quandles, okay? So we call the involutory quandle diquandle. Then we have this theorem. A G2 family of quandles gives an involutory quandle, diquandle, and vice versa. Proof is easy. G2, we write the group G2, 1 and -1, and let this be a G2 family of quandles. Then we define two binary operation delta 1, delta 2 like this. Okay, in this case, delta 1 is x the star 1, and delta 2 is x star inverse y, or x delta 1 while x star inverse y and x delta 2y x star 1y. Then delta 1 delta 2 is involutory quandle diquandle. That is easy check. And conversely, these two are be any involutory quandle, this one or these two, with the trivial operation star and the involutory quandle operation delta. Then these two operations like this. Then this is the G2 family of quandles. So special class of diquandle is just the G2 family of quandles. This is some basic definition, homomorphism and isomorphism, okay, as a user in quandles and also biquandles. Let delta 1, delta 2 be a diquandle. The flip of this diquandle, that denoted by this one, is defined by x delta 2 and delta 1. Actually change the role of the two operations, the same set with interchanging the first and the second binary operation. Then by definition, every flip of a diquandle is also diquandle. Okay? The diquandle x is said to be self-flip if x and the flip of x are isomorphic. We consider this example, x is 1 to 3 with the matrix M1 and M2. Then M1 is a self-flip, okay? These two matrices are the same. But the matrix M2 is not self-flip. Okay? And x delta 1 delta 2 be a diquandle, and delta 1 inverse delta 2 inverse be the dual operation. Then for all labels 1 2 and x y z, we have these identities. Okay? These identities are also hold. And also delta 1 delta 2 with the two quandles, and delta 1 inverse delta 2 be dual operation. Then if these operations satisfy this one, so we use all dual operation here. Okay? Then we have these identities. So we use this is delta j and this is delta k, inverse to dual operation. J and k is the same or not. So whatever, these identities are hold. These identities holds. So the diquandle axioms dq2 and dq3 are equivalent to the axiom dq2 prime and dq3 prime in the above theorem C. This means we can use these two identities as the axiom of the definition of diquandles, okay? All dual operations. So now the final sections. Let D be an oriented dichromatic link diagram, and let R of D denote the set of all arcs of D. And let X delta 1 delta 2 be a diquandle with a dual operation delta 1 inverse and delta 2 inverse. Then diquandle coloring of D by X, or simply diquandle X coloring of D, is a map from the set of arcs to the diquandle X, such that at every positive and negative crossing, these coloring relations are satisfied. Okay? So this is the label of the component I and J. Of course, I and J are equal or not, and 1 over 2 also. Then this is a positive crossing. At the positive crossing, the coloring satisfies this rule. So this J delta J operation contribute to these labels here. So actually the labels determine the operations delta 1 over delta 2. And the negative crossings that we have this coloring rules at each crossings. Then the diquandle element is called the color of the arc S, and the pair diagram D and this diquandle coloring is called X-colored dichromatic link diagram. And as usual in the quandle and the biquandle, the set of all diquandle X colorings of D is denoted by this notation. Then we have this lemma: D and D prime be two oriented dichromatic link diagrams in R2. They can be transformed into each other by oriented generalized Reidemeister moves. Actually, dichromatic Reidemeister moves. Then for any finite diquandle X, there is a one-to-one correspondence between these two coloring sets. Proof is very easy. It's sufficient to prove the adjustment. The D prime is obtained from D by a single oriented generalized Reidemeister move. Then this picture shows there is a one-to-one correspondence between two sets of colorings. Okay? Actually, Reidemeister move 1 is this one is X. Okay, delta I is also quandle operation, and also delta I inverse is a quandle operation. This one is equal to X. So Reidemeister type 1 does not change the coloring numbers, and similarly R2 and R3 also does not change the coloring set. Actually, the colorings of this move determine the unique coloring of this move, okay, and vice versa. Then we have the theorems. We have these theorems. L be an oriented dichromatic link in 3 space, and let D be a diagram of L. Then for any finite diquandle of X, the cardinal is the invariant of L. So proof is immediate from the previous lemma. And if X is a finite diquandle, we call this number is a diquandle X coloring number or diquandle counting invariant of L, and denoted by Gx of L. So Gx of L is just the cardinal number of this one. Finally, we introduce 2 examples. Consider these 2 dichromatic links of 3 components. Okay. Look at these examples. The underlying diagram is same, but the orientation is changed, right? The label is 1, 2, 2, and 1, 1, and thus the orientation is changed. Consider X 1, 2, 3, 4, 5, and diquandle with this operation table. Then from these diagrams, we can find the coloring set like this. Okay. Actually, each crossing gives this identity, as usual in the quandles or biquandle case. At a similar one. Then the number of this set is 35, and the number of this set, the element of the number of elements of this set is 29. So the coloring, 2 coloring numbers are different. This means these 2 dichromatic links are not equivalent. Actually, this example shows that the diquandle coloring number detects the change of orientation of each component of a dichromatic links. Another example is consider 2 dichromatic links with 2 components like this. Now, comparing these 2 diagrams, the underlying classical link diagram is same, but the component labeling is different, right? This component is 1. The label of this component is 2, but in this diagram, 2 labels of the components are changed. Consider these diquandle with order 5. Then the coloring set are given by this one. Computing the number of this coloring gives GYD, the number of element of this set is 19, and the number of this set, the number of elements of this set is 25. So these 2 dichromatic links are not equivalent. Actually, this example shows that the diquandle counting invariant detect a change of the labeling 1 and 2 on each component. Our final example is some more computations are shown. These are 8 oriented dichromatic links that introduced the previous page, maybe this one. So we compute the coloring number of these 8 dichromatic links gives these tables. So this table shows that the diquandle coloring numbers distinguish these 8 oriented dichromatic links by using 2 kinds of diquandle. And this one and this one, X and Y. This is the end of my talk. Thank you for your attention.
Yeah, thank you very much. So please, questions, comments, remarks. I have a very simple question. So you considered coloring with 2 labels.
Yeah.
Do you think it is reasonable to consider more labels?
Yes, yeah. That is a very
It is
natural
reasonable or not?
questions. Yeah, maybe it's reasonable, but we can define the similarly.
Yes.
Yeah, labeled quandles. Yeah, but it's very complicated, but it's possible. Yeah.
Okay, please, more questions?
I have a question.
Please.
Yeah.
Would you show me the last example,
Yes.
2 component?
2 components.
Yes.
This one?
This one, yes.
Yeah.
But this one, the left one, the first component is trefoil.
Yes.
And D prime, the first component is trivial knot. So it's easy to distinguish.
Yes,
In
sure.
the quandle level. So I'm wondering, they are distinguished by quandle, diquandle. First operation is, for example,
Yeah.
dihedral quandle.
Yeah, this example, the purpose of be used to distinguish the dichromatic links, and also in particularly the component labels. If we change the component labels, then
yeah, I know.
Yeah,
But how about this? Consider quandle, diquandle. And
quandle,
yes,
yeah, maybe also possible.
First operation is R3, order 3 dihedral K. And the second operation is trivial quandle.
Yeah.
Then we can distinguish D and D prime easily.
Okay, yeah, maybe possible, yeah.
So I'm wondering the example which cannot be distinguished by quandle, diquandle.
Yes. That's a good question. Yeah, but I didn't find such examples. Yeah. I know.
The 3 component is very interesting. Could you show us the 3 component?
3 component.
Yes.
Maybe.
The figure.
Yeah, figure. 8 examples.
Yeah. You change the orientation.
Yeah. Where is the examples? Oh. Dichromatic. Here, yeah. Three component is
Yes,
this
6,
one.
1, 3, and
Uh-huh.
you change the orientation, then you can distinguish them. It's very
Mm,
interesting.
yeah, I didn't calculate it that once. Mhm.
Thank you, thank you.
Yeah, maybe possible. I think we can find some using some special diquandle. Then we can distinguish it. Yeah, such a case. But I don't know.
Thank you. More questions, please. So I suppose you can describe situation when you cannot distinguish, yes? Some kind of, if you have symmetry or something like that.
Yes.
So maybe you can say something like,
Yes, yeah.
classify cases when you can,
Sure.
definitely cannot. Okay, so more questions, please. Okay, if there are no questions, so let us thank speaker again. Thank you very much for interesting talk.